In the Addition of Vectors lab, students use a force table, like the one here, to measure the forces which combine on this small ring in the middle to hold it in equilibrium. They'll then graphically draw those vectors on graph paper and show that they balance.
If the force table was set up with 4 pulleys on the edge, simply remove one of the strings, and if you wish, disconnect the pulley and use the remaining 3 for the experiment.
The center ring is connected by strings, pass over pulleys, and are attached to mass hangers. Students hang mass on a pair of the hangers, record the position of the hangers measured around the rim in degrees, and then determine what compensating force is necessary on the other side, in a third hanger, to balance the other forces on this ring. So they will add enough mass to the opposite side to get that ring to balance so that it's in equilibrium. And when displaced, it doesn't accelerate. In order to do this, they may need to adjust the angle of their balancing force so they can control the magnitude and the angle. And once they've found a system that keeps them in equilibrium, they will record the amount of mass hanging off of each mass hanger, thereby knowing the magnitude of the force, and they'll record the angles. To estimate uncertainty in this lab, the students are going to find that the uncertainty is dominated by essentially friction in the pulleys, so that even for a different amount of force, they may find the system appears to remain in equilibrium. Okay, so they can try adding smaller and smaller increments of force, or increments of mass, to the balancing mass, looking for the smallest increment which doesn't affect the equilibrium state. So it appears this 5-gram mass doesn't add enough tension to the string in order to overcome the static friction in this pulley and displace this from equilibrium. Since the purpose of this experiment is to show vector addition, it's important that we consider uncertainty in not only the magnitude but also the angles of the vectors that are recorded. So the center ring here, which is in equilibrium, may or may not be centered on the center post. And in particular, if it's off-centered, then the angles that are read by the tick marks on this scale may not actually correspond to the direction of the string, if the string is not pointed radially out from the center post. So they can estimate 1 or 2 degrees of uncertainty in the angles and consider that, as well as the uncertainty in the mass they have from the additional mass that causes the system to sway from equilibrium. For the analysis of the first experiment, students will transfer their measured values for the vectors onto a piece of graph paper using a compass to keep track of the angle and a ruler that they use to ensure that the length of the vector drawn is proportional to the magnitude of the force that they measured. So they'll have vector 1. From the tip of vector 1, they should draw their next vector in the appropriate direction with the appropriate length. We'll call that vector 2. And of course, the sum of vector 1 and vector 2 is found from the tip-to-tail method. And they can draw that on the graph as well if they choose to. We'll call that vector 1 plus vector 2. Now they measured the balancing force, and that balancing force should be equal and opposite to the sum of the 2 independent forces. And so starting at the end of vector 2, they can draw the balancing force. So they'll use their protractor to draw that force in the direction that they measured it. Use the ruler to ensure that they draw it with the measured, or length proportional to the measured value. And what they will likely find is that it won't exactly be equal and opposite to the sum vector. But if they take into account the experimental uncertainty in both magnitude and angle, they should find that this balancing force encompasses this point. Okay, so to include the uncertainty in angle, they can simply find the range of angles, and the uncertainty in length can be used to determine a range of lengths, and an ellipse can be drawn that's within that range of angles and that range of lengths. If that ellipse encompasses this starting point, then the balancing vector is equal and opposite the sum vector within the experimental uncertainty. If it does not, then of course it does not show that the force is balanced. And as I've drawn it, it's only marginally equal. And they can use that to give some quantitative statement of whether or not they showed that the force is balanced. For the second part of the experiment, students will use the same data to draw the same three vectors, but rather than drawing them tip to tail, they will draw them spaced out on a separate piece of graph paper. Now they're drawn with the same directions relative to the axis of the graph paper that they had in the original diagram and that they had in the force table. And they can be drawn with the same length, or if appropriate, a new scale factor can be drawn, and they can be labeled the same way. But since they're not adding the vectors graphically in this part, but rather adding up the components, they're going to graphically find the components of these vectors, v1x, v1y, v2x, and v2y, and components for the balancing force as well. Now the balancing force is where we've included the experimental uncertainty, and so when determining the x and y components of the balancing force, they should use the measured vector length as well as the projection of this uncertainty ellipse onto the x and y axes to be able to say that there's a y component and an x component to the vector itself. There's also some uncertainty in the y component and some uncertainty in the x component that they can include in their mathematical description of the vector lengths. The lengths of each of these components will be measured, and the same scale factor that they used to draw this will be used to convert this back into a force. And with the forces that represent the x and y components of each vector, including the uncertainty in the balancing force, they can say whether the sum of the x components equals the balancing x component within the experimental uncertainty.